So what we had seen was reversible isothermal work, and we saw that in case of an expansion of an ideal gas, the maximum amount of work that can be derived from the system is equal to the reversible work, right? And which was equal to W is equal to minus of RT log V final by V initial, right? Or I don't know if there was a number of moles. Fine. If you deal with number of moles, of course it's got to be there. The same holds true. Since it's reversible, I can also compress the system in the same manner. Since it's reversible, I just have to reverse it. Instead of expanding, I start contracting. So the reversible work in case of compression would exactly be the same, except that its sign would be changed. Yes? Because the final volume would be smaller than the starting volume. Yes? The only thing is that if I try to do irreversible work, it would be more than the reversible work. That means in case of expansion, I get less work out of the system, but in case of compression, I have to give more work to the system. And since it's an isothermal process, delta U is 0, right? Everything that is lost is heat. Yes. You need to lose some heat when you do it in an irreversible manner. So I leave it to you to understand how this heat is lost. You would go ahead and worry about what exactly you wish to do. Okay. Now, coming back to the state function, the internal energy, right? We would need to calculate the work done, the heat loss. In this case, in case of the isothermal process, in the reversible process, whatever the amount of work that was done by the system is equal to the heat that has been input into the system, because delta U is 0. Okay. Normally, otherwise, delta U is dq plus dw. That's the first law. We all know this, right? And dq, right? This is at the heat capacity, right, which is dependent on the path, okay, times dt minus the external dv, right? That's how you normally state this. So this, well, you already know in case of the kind of work that, the kind of systems that we're dealing with, this would be CV, right? Heat capacity of constant volume. We'll come to those things later. Now, how we get into that is, let's write U. Now, if you see, U depends on two variables, temperature and volume, right? So U definitely is a function of these two variables, temperature and volume. I could have chosen some other variables, that's fine, right? But these are the natural variables that come. All these variables are connected, right? U is a function of temperature and volume, and I know that pressure is a function of temperature and volume, so I could have written U as a function of anything for that matter. Because pressure, temperature, volume are also connected by the equation of state. We choose these two variables because it's more natural to choose these. And if I do that, then I can write that du, a change in U, yeah, like we saw this three-dimensional graph. So U is plotted on the z-axis, E is plotted on the x-axis, and V is plotted on the y-axis. Fine. So a change in U would depend on a change in the volume or a change in the temperature, right? What would it be? In case there is a change, in case there is any change, the way you show a change is, let's say, U as a function of temperature, okay, and let's say that's the plot of U as a function of temperature at constant volume. You're not changing the volume. Then if I want to say what is the change, delta U is equal to slope times delta T. That is what I would normally say. Yes. If my slope is constant. Yes. It is in a limit when delta T is very small, I could write du by dt is equal to the slope, right? Or if I really want to be precise, then I would write del u by del t at constant V is my slope. So all I need to do is to replace that over there. Delta u is equal to sorry, no more slope, but del u by del t at constant V times delta T, right? Yes. And now I say, okay, I want very small increments. So what I'll write, to be very, very precise, would be du is equal to del u by del t at constant V times dt, right? The same thing would be true when I change volume. So if I do that, now if I change volume, then my expression for du would be del u by del V at constant T times dV. Yes. I can, now the thing is, I could change anything at will, either volume or temperature. Why I can do this is because these two variables are independent of each other, right? Only then I can do such things. So what I can write, if I can change it at will, is du is equal to del u del t at constant V times dt plus del u del V at constant T times dV. And if I compare this with the previous equation that I just wrote, C of path times dt plus, yes. So let's say up to here it's clear. Yes. Okay. Now whether I change along the volume axis or I change along the temperature axis, I will get a change in U. Right. I choose. No. Yeah, what you are saying is fine, but it's not that. Du is a very small number one. The thing is that, look, du, that way it's not mathematically, because du is the change in U. Okay. So if temperature changes and volume changes, still I call it the change in U. Right? Okay. So what we can associate this fellow is this fellow over here. That's the heat capacity, and it's at constant volume. So we call this CV, right? This fellow is something we don't know. Well, for the moment, we don't know, but from your previous knowledge, you all know that this is 0 for an ideal gas. Yes? Because you know that for an ideal gas, du depends on the change in temperature. Right? And why? Well, the reason is really simple, because the gases, ideal gases, do not interact with each other. So no matter if I take them far apart or I bring them close enough, they don't interact. If they don't interact, then volume should not have an effect on the internal energy. Right? Those attractive and repulsive forces that I showed you, that Leonard-Jones potential kind of thing that is going down and then being very repulsive at close separation, when they are very close enough, that is only for real gases, not for ideal gases, right? Ideal gases don't interact. No? So that term is not given for ideal gases. Now, we call this but there must be some way to actually, since we are dealing with real gases, in that case this term should not be 0. So there should be some way to actually evaluate this. Okay. Now there is a very nice experiment by Joule. It's called the Joule's expansion. He devised this experiment to evaluate the constant which we term as pi t. Now, I don't know if I should show you the experiment first, or should I derive the maths first? Maybe let's try deriving the maths first. The idea is that if I want to find this, I need to ensure that we do it under a certain set of conditions, so that there is no change in the internal energy. Okay. Okay. Maybe it's better to show you the experiment. The experiment is it's like this. So take an insulated container. Okay. And let's say we have some gas over here, and we have vacuum over here, and this insulated, so let me make it insulated by drawing a double wall. And what we have is water filled in. That's what Joule did. So that's Joule's expansion. Okay. So this fellow does not exchange any heat from outside. This kind of container, it's adiabatic. So if it's adiabatic, then for all we know, okay, so since this fellow is adiabatic, then Q is equal to 0, right? The work done is minus P external dV, right? What's P external? This is a stopcock which I am going to open, right? So it's expansion against vacuum. So the work done is 0. So if both Q and W are 0, delta U or du, whatever you wish to call, is 0. Right? Agreed. If that is the case, then Cv dt plus del u, a bit of maths is what we require over here, del u by del v t dv is equal to 0, because this is equal to du. Yes? Great. If such is the case, then All I want is to evaluate del U by del V at constant temperature, right? Del U by del V at constant temperature times dV is equal to minus of Cv times dt. Yes. And if I take dV on the other side, I simply get del U by del V at constant temperature is equal to minus Cv del T by del V at constant what? What is constant? I heard it somewhere. Good. Say it loud. See, we have put du equals 0. Constant internal energy. Right? We cannot say constant temperature because we are now not assuming that things are ideal. So be very careful with that. So this is at constant internal energy. Right? So what I am going to do, I am going to measure essentially the change in, now if I see this setup, I have already made sure that this is constant internal energy. What I am going to measure then is the change in temperature as a change of volume. Let's change a small volume. We can start with small gas balloons over there, change a very small volume, keep on increasing it, and see if there is any change in temperature. Okay. Of course, for an ideal gas, you don't expect it. The interactions are not there, so this should be 0. Anyway, this should be 0, right? So that delta T by delta V should also be 0, right? Yeah, this fellow also has a name. So let me just write it down. This is eta J. So the Joule coefficient. Anyway, so pi T is equal to minus Cv times eta J if you wish to write it that way.
So we have felt that gas balloon in water. So the temperature of water will also increase. Water is also coming in the system.
So that is what he did was to put a thermometer over there to measure the temperature of this water if there is any rise in the temperature. Right?
Instead of constant internal energy, we should write constant pressure.
No, pressure is not. Pressure will change. Once I expand this gas, the pressure is going to change. The final pressure will be something different start and the initial pressure is different. But the internal energy, because this is an adiabatic container, one thing, right? So the internal energy of the whole container is what we are talking about, not just the balloons. Okay. So what is expected is essentially that since there is no exchange of heat from outside, I am not allowing any heat to escape or any heat to come in. What you expect is that there should be some change in temperature. If the heat is retained inside, that heat will cause the molecules to move more randomly, right, at larger speeds. If these molecules are moving at larger speeds, that means it corresponds to a higher temperature. Maxwell-Boltzmann distribution, nothing different, right? So, what I am expecting is that all the heat is retained inside and there is going to be some change in temperature by doing this. Okay. Now, the thing is that Joule used water and a large reservoir of water. Second thing, water has a huge specific heat. Huge specific heat. So, what does it mean? What does specific heat mean? That can I raise the temperature of this fellow or not? Can this material accommodate heat into it or not? If the specific heat is high, then yes, it can accommodate heat without increasing the temperature. If the specific heat is low, then the temperature increases being supplied to this system. Water has a high specific heat, right? So, and these temperature changes, these molecular interactions are low for the gases that he measured. So what he actually observed was that there is no change in temperature as a function of volume, right? So essentially, what he came to the conclusion was that this fellow is equal to 0. Well, very true, it's 0 for ideal gases, but this is not 0 for real gases. The only limitation was the limitation in measurement. After that, there have been improvements in the design, and you can get the the values of Joule expansion coefficient. So they're small, but still you can measure it. But this was the first attempt, and yeah, he could not do it.
So can you explain how we have changed that volume when we how we measured when we changed the volume? What kind of volume and what volume?
So we've expanded the gas, right?
Yeah, like Delphi is there.
Right.
If we can tell the energy constant.
Right.
So can you explain that?
See, what we had was these two balloons over here. I guess these were made of metal or something. I'm not sure about the experiment. What I remember is he used the pressure of 22 atmospheres. But anyway, what you have some gas on this left part, and you don't have anything over here, vacuum. And suddenly you open this top box. Now the volume, if these volumes are equal, then it's double. So you want to see if there is any temperature change, which he could not observe. Limitation of the experiment, okay, not limitation of the science, but it's a limitation of this experiment because this fellow had a large specific heat, the entire reservoir, so it could not change its temperature because this fellow has given a very small amount of heat, right? Yes?
So here, can we say that it is expansion against vacuum?
Yes?
So, because vacuum is just momentarily, just initially, just when the gas starts moving, the rest of the gas has to expand against some pressure because some of the gas is already gone into that.
Yes.
So it's not completely a vacuum.
But that's what expansion against vacuum is, right?
So
That
when
is
we
taken into the system.
That's taken.
so when we use the piston,
It's the same thing.
no sir, then it's always closed and external pressure is always zero. That's fine.
No, but I have a set of two stops on top. So what you would say is that this piston flies immediately to the top position. Yeah? Yeah, some gas comes over there, so there is some pressure developed, that's what he said.
You're calculating it for the whole system.
Calculating it, exactly. You're calculating it for the whole system. So it's exactly in the same case of pistons also, it's the same thing. Yeah, we can have a parallel session, but outside the class, if you wish. Yes, tell me. Yes. No. This entire thing is adiabatic, right? This is the adiabatic boundary.
So, but the expansion against vacuum, when the peak shell is zero, they can be some heat exchange from water.
So, I'm not saying that from here to here. So, this is not my system. My system is this fellow. The entire box is my system, not just the two balloons. Okay. So there is no heat exchange from outside into this. Right?
So
Yes, there is a heat exchange from the balloons to water, and that is what I wanted to check by measuring the change in temperature.
Here we have taken a term CV. So is that still only gas or water and gas combined?
Yes, very much.
So what's the difference between del and d?
Okay, so the difference comes only when you have a dependence on more than one variable. Okay, like I showed you over here. Initially I had written du by dt, right? Over here I had initially written du by dt, and then I said let me be more precise and write del u by del t at constant v. Okay, so what del means is partial differentiation. Okay, so I'm holding all the other variables constant but differentiating only with respect to one variable, that is temperature over here.
So if we are considering the whole system of water plus the gas, then what is the volume change that we are talking about? The volume of the whole system remains constant, the gas volume is
No. And yeah, the volume of the whole system remains constant, that's true. But where's the work? The work that has been done, how am I calculating that work? Yeah, so I'm not changing the volume of the water or anything, and I'm not calculating any work done on water. That's fine. Fine? Or some more questions on this? Or it's fine? Okay. So, Joule was not able to observe this, but it does exist. Later on, we'll show mathematically that this fellow is equal to 0 for ideal gases. But you understand, physically you understand that since they do not have any interactions, it doesn't matter how close they are. Right? It doesn't matter what's the volume of the gas, whether it's small or large, there is no effect of this for the ideal gases. Right? Let's come to a concept which is even more important than the internal energy, and that's enthalpy. Why it's more important is because our everyday processes that we do, they all occur at constant pressure. Right? Whatever activities you think, they're not at constant volume, but they are at constant pressure. So let's define enthalpy. With the symbol H. Okay. So let's say there is some process, let's say we have a gas A which is at pressure P, temperature 1, volume 1, and at constant pressure there is a change. So since we are talking of enthalpy, it stays at pressure P, temperature 2, volume 2. That's a reversible constant pressure, right? And let's calculate the change in internal energy. The change in internal energy would be just from the first law, Q plus W, which is equal to Q. This is the heat exchanged at constant pressure, right? So let me write this as QP minus P external dV right? Or if you want to already, since I am taking delta U over here, so let's already integrate this fellow. instead of dV, let me just write delta V. My V's and U's sometimes get confusing. Yeah, okay. It's from, if you want to call it from state A to B, or let me just write that this is some gas in state A, this is the same gas in state B. If I bring this fellow over here, then I have delta U plus P delta V is equal to QP, right? Or I could bring this delta out and write delta PV, right? Instead of this, I could just write delta PV, because pressure is constant. This would be P delta V plus V delta P, right? And V delta P would be 0 since pressure is constant, and I could then write it like U plus PV is equal to QP. Or from the definition, let me just define that this is the enthalpy. Let's just define U plus PV is the enthalpy.
We started with PSP external and ended up. We started as PSP external. So when we are defining PSP external.
Very good. Where's the catch? Yes? Good. Okay. So that's what essentially the definition of enthalpy is. And yeah, something. And if we look at it, then enthalpy we can we can choose functions like temperature and pressure for enthalpy. Right? Now, if I do that, then I can write the change in enthalpy would be the change of enthalpy with respect to temperature at constant pressure times dt plus change of enthalpy with respect to pressure at constant temperature times dP. Just as we write for state functions, just as we wrote for the internal energy, the same thing I can write for enthalpy. And now we have to worry about what exactly these things are. What exactly del H by del T at constant pressure is? Well, of course, since del U by del T at constant volume was Cv, you know, there is a change in enthalpy with temperature. Right? So that is Cp, heat capacity at constant pressure. Plus, we have something. We have something over here. We'll just discuss about that. Maybe I could just write this as it's not J, it's T. Sorry. Mu T. We'll talk about what mu T is. But essentially, if I look at this thing, then I know that my dH at constant pressure is nothing but the heat exchange, right? And that is a more natural definition of the heat capacity, right? So from here, what I can write over here is that this fellow, if I choose constant pressure, if I just say then dQp is equal to Cp dt. That's what your definition of heat capacity is. The amount of heat that it can take per unit temperature. Remember, all these CV, CP, they are defined for a particular temperature. They are a function of temperature. And the good part about these CP and CVs is that they are fairly constant over a narrow range of temperatures. So most of your thermochemical calculations that you do are over narrow ranges of temperature, and then you don't have to worry about the dependence of the heat capacities on temperature. Okay. If the temperature range is large, then of course you have to worry. Right. So let's worry about yeah.
So why is the difference? Why is the
Q is always an inexact differential. We say exact or inexact depending on whether we can integrate it without the knowledge of path or not. Yes. Since the heat or work, heat absorbed, heat emitted, or work done on the system, done by the system, everything, they are all path dependent properties. Their integrals would be path dependent. It would depend how exactly. See, I just put that cut to make sure that you remember that it's inexact. That's not, sometimes I can forget it. Don't bother about it, but it's always inexact. That's why you never write delta W or delta Q. Right? Delta is associated when it's a change from one state to the other. When I can calculate W2 minus W1, then I can say delta. But when I can't, then we just write W and Q. Okay, so let's worry about mu. Any other question on? Yeah, then let's worry about what this mu T is. Okay, now like you had the change in the free energy with respect to volume, del U by del V, which was the Joule expansion coefficient or the Joule coefficient. Now, this fellow is changing enthalpy with pressure. And again, we'll derive it later, but this is 0 for an ideal gas. Okay. Well, you all know that the enthalpy depends only on temperature for the ideal gas. Okay. So definitely that fellow is 0 for an ideal gas. But it does have some value for real gases. And this, to determine this Joule-Thomson coefficient, what we did in case of determining the Joule expansion coefficient was to choose a system which was not adiabatic, it was constant internal energy. Here we'll have to choose a system which is constant enthalpy, right? So the system is that we have to choose is called enthalpic. And mind you, this was a work of tremendous genius by Joule and Thomson. Okay. This is the Joule-Thomson coefficient which we are talking of. In the way I have written it, mu T, that is del H by del P at constant temperature, it's called the isothermal Joule-Thomson coefficient. There are two types of Joule-Thomson coefficients. So mu T is equal to del H by del P at constant temperature. It's the isothermal Joule-Thomson coefficient. What Joule and Thomson measured were not the isothermal Joule-Thomson coefficient, but mu, which is equal to del T by del P at constant enthalpy. which is the Joule-Thomson coefficient. I'll show you in a short while that both of these are related. They are just related by minus Cp times mu is equal to mu t. So you'll find various names. Sometimes they write mu jt, sometimes they write something, but I think this is the convention that Atkins follows, so we'll just stick to that. So now you want some experimental conditions which ensure that there is no change in the enthalpy of the system. Okay, and this was really, if you look at the experimental arrangement, you'll understand that it's really a work of genius that somebody could actually think of such an experiment. So let me take some time and draw this schematic over here. Again, we have an adiabatic system. Adiabatic. Okay. Just give me one moment. So what we have over here is an adiabatic boundary all over. Okay. I'm just not drawing it on these sides because it will be difficult to pull and push the pistons, but it is there. And on the left side, we have some gas. Well, of course, it's got to be a real gas. Yeah. Otherwise, in the case of ideal gas, I cannot measure del H by del T at constant temperature. So this is at some pressure P1, T1. This fellow inside is a porous plug. Okay. So that's a porous plug or a throttle, whatever you wish to call it. The gas can go through it, okay, but there is some opposition, so it can't go through freely. So what the experiment is doing is to send all of this gas from the left to the right. Okay. What is being done over here? This is a porous plug, so it can create a pressure difference on the two sides. Right? Kind of a throttle, a kind of a tap, if you wish to think of it that way. Now, from the left, I'm pushing with this piston. The external is P1, which is the pressure inside, which means that this fellow and this fellow are in equilibrium. Okay, so from here to here it's reversible, right? But so I have to push it hard enough so that these two things stay in equilibrium. But I don't have to push it so hard that the porous plug doesn't act. Right? So gas on the other side must be at a different pressure, not at P1. That's what the work of this throttle is, to maintain a different pressure. So this fellow on the right is not. So slowly what will happen is this will come in and this piston would move out. Right? So remember, the left side and the right side are not in equilibrium. Right? The pressure over here is P2. But yeah, I just missed that P2 external over there. This external pressure is also P2. So this fellow is in equilibrium with this fellow is in equilibrium with this fellow. To start with, we had nothing over here. To end with, we had nothing over here. Now, let's calculate what this is adiabatic, right? It's adiabatic. So Q is 0. Start with. So adiabatic Q is equal to 0. Straightforward. Now, what is the work done? What is the work done from here? If the piston goes from here to here at an external pressure P1, minus of P1 into V1 minus 0. No, final is 0. So 0 minus V1. So plus P1 times V1. So work done on the left side is equal to plus P1 times V1, and work done on the right side would be, it goes from 0 to V2 and the external pressure is P2. So minus of P2 times V2. Great. So the initial pressure was P1, the initial volume was V1, final pressure is P2, final volume is V2. So this is actually minus of delta PV, right? Okay. So let's get back to the first law. Delta U is equal to Q plus W, which is equal to minus of, so 0 minus delta PV, right? Q is 0. It's adiabatic, Q is 0. So it's just, I rearrange this and get delta U plus PV is equal to 0, or delta H is equal to 0. Imagine, I mean, you can imagine the beauty of this experiment. How this porous plug has been designed so that you can actually maintain isenthalpic conditions. Huh? Don't you think this is some kind of a genius at work? No? You got to appreciate the experiment, huh? Then you would understand that. Yeah. The rest is simple mathematics. Now, do exactly the same thing that you did for du. Just write dH is equal to, okay, del H by del T, that we already know is Cp times dt plus del H by del P at constant temperature times dP. Yes, and this is equal to 0. And what I get out of this would be that del H by del P at constant temperature should be equal to minus of Cp del T by del P at constant enthalpy. Yes. right? This is what I said was the Joule-Thomson coefficient, not the isothermal one. Yeah.
If we don't have constant enthalpy, then we can't use this formula.
And that's why they had to design an experiment where they had constant enthalpy. Now there's something I've just drawn on the blackboard, but that's not the case. They've actually designed this. They actually made some. This was more like a cylinder. Some of the original photographs are there, which you can have a look at. And inside the cylinder is divided into two parts. I think it's more or less concentric. So one of these things is a porous plug. Inside that there is gas, outside there is nothing, and then slowly this thing is pushed in. So very interesting experiment to see. But this is what they measured. So what they measured was essentially the change in temperature as a function of pressure, keeping enthalpy constant. Right. Of course, this is the Joule-Thomson coefficient, and this has a lot of practical applications also. But for an ideal gas, you can actually calculate. Okay.
So can you please explain the functioning of that porous thing?
So going back over here, so the pore is something that would rather obstruct the gases. So it would create a pressure differential between the left side and the right side.
So can you design that on a microscopic level? Can you show it on the board how actually it's a how do we get the fields?
A porous plug, a zeolite, for example, some of those things. I'm not sure what they use, but anything which is permeable to gases but not completely permeable. It does oppose some movement of the gases. Right?
So how much does it come?
No, it allows movement, right? But not at the same rate. So if I'm sending 100 molecules, then it's allowing only 80 to go through at that moment.
Is it varying with the pressure that
Yes. Would be, I guess, proportional to the pressure. That's why I said you don't have to apply so much pressure that everything goes in. Because if you apply too much of the pressure, then these pores would allow all the gas to go in. So you could think of something of this sort, the chair that you're sitting on. This has some holes. And if I put some water on top, then it will allows the water not at the same rate to go through. That kind of a thing, nothing more. Even a wall, for example, a concrete wall allows gases to be exchanged, although at a slower rate. So zeolite or clay, for example, don't quote me later. I'm not very sure what the material is. Okay.
So how does this slowing down of the gas movement?
If this were not there, then whatever I do, the pressure on the other side would be P1. Right? But now I've managed to slow down. So less number of molecules would be hitting here or here, wherever. Right? Which means the pressure is reduced over here. Lesser amount.
People is not taken. People is not taken.
It should not be P1. That's what. If it is P1, then this would be V1. and this would be anyway 0, things would not work. Hmm?
So I don't understand why work we are written as W
So the work done is P1 V1 minus 0, P1 into V1 minus 0, oh, V1 0 minus V1, sorry. So what's work? So let's write here again P1 into V1 minus 0, no, yeah, or let's write the way we are doing it. So minus P1 into 0 minus V1. This is the work done on the left hand side, and the work done on the right hand side would be minus P2 into V2 minus 0. That's all. Okay. So for an ideal gas, the Joule-Thomson coefficient is 0. Let's calculate it for a van der Waals gas and see what are the practical applications of this Joule-Thomson coefficient that we have over here. Okay. So for a van der Waals gas, now I'll give you a starting point, okay, which we'll come to later. You'll be able to, once you have all the mathematical tools in hand, only then you'll be able to come to these things. But this comes out to be B minus A by RT. Okay. So the isothermal Joule-Thomson coefficient in case of a van der Waals gas is B minus A over RT. Yeah, approximately. The rest of the terms are higher, so we can ignore them. Okay. So if it comes out to be B minus A by RT, there must be some temperature at which this fellow is 0. And there's a slight difference. There's a term of 2 somewhere. Okay, this is not Boyle's temperature. This is called inversion temperature. Okay. So if this is equal to 0, I just need to find that temperature T is equal to T inversion, what I call, which is nothing but A over RB, right? Okay. Now remember, A is the attractive term, B is the repulsive term. So, if I am above the inversion temperature, right? If I am at a temperature that is higher than the inversion temperature, then I would have my repulsions dominated. Gas molecules would tend to fly apart. If I am below my inversion temperature, then my attractive term would dominate. The gas molecules would tend to come together. Yes. In molecular terms, what you would say is, if gas molecules are trying to come together, that means some of the molecules are attracting them, which means their average speeds are reducing. If their average speeds are reducing, there is a fall in temperature. So, below the inversion temperature, or gas cools below the inversion temperature, right? So what would happen if T is greater than A by R? Which term is dominant? A or B? Why? You said B. From the equation, right? No. If T is greater than B dominates, right? If B dominates, that means we are in the repulsive regime. Yes. If things repel each other, that means the molecules are going away from each other. If things are going away, so if I have two things together and one of them is sent away, that means its speed increases. If things are brought closer, then see this molecule is flying. All of these molecules are moving, but I have some attraction over here. Right? So this fellow is going, and there is some attraction over here. So this will be slowed down. If there is repulsion, it will go fast. It will go away fast, right? That's the only. So if there is repulsion, the speeds increase. If there is attraction, the speeds decrease. If the speeds decrease, the temperature drops down. If the speeds increase, the temperature goes up. Right? That's all. Nothing. So
So I did not understand how temperature is basically at a greater temperature with heat dominance.
what do I do? Anybody else who doesn't understand if we are at a higher temperature, we dominate? Wait. Look at this equation. T is equal to A by RB. If this is large, what do I expect? If this is large, what do I expect? This term is small. Yes? If this fellow is large, then this term is small. B dominates.
Well, sir, if differentiated double square inversion temperature repulsive forces dominate, then if P inversion double square means that either A should be higher or B should be lower.
For a gas, A and B are constant. Fixed. You can't change that. Okay. Now the only thing is that at the inversion temperature, this thing is 0. If I am at a higher temperature, then this term is small. This dominates. If I am at a lower temperature, then this term is large, so this dominates. That's all. That's all what I mean by attractive terms dominate or repulsive terms dominate. At T inversion, exactly they cancel out. See, let's say there's one molecule over here and another molecule passes by. If this fellow attracts, right, the speed of this molecule will be slowed down. And the speed is directly proportional to the temperature. Maxwell Boltzmann just if I am wrong, you can correct me in a moment. So let's finish this. On the other hand, there's repulsion, then this fellow would come and This would be repelled. This would go through very fast. In that case, the speed would get enhanced. It's just a distance. It's not coming from you. So this is very much basics of our van der Waals equation which we did in the last class, right? B was the volume of the hard spheres, right? And because it's essentially a hard sphere, the other molecule cannot penetrate this hard sphere. It's kind of a repulsion. A, on the other hand, was associated with the proportionality factor of collisions. This was the frequency, right? So this would then be the term that causes the attraction. Right? Yes. So yeah, speed is directly related. Yes, yes, yes. नहीं हम ये कह रहे हैं, हम देखो हम टेम्परेचर नहीं बढ़ा रहे. What we are doing is, if I am doing this experiment, what happens to the experiment? Yeah. If I am doing this experiment at a temperature which is greater than the inversion temperature, then the gas will warm up. If I am doing it at a temperature lower than the inversion temperature, the gas will cool down. That's all. I'm not changing the temperature on the, okay? There was something. So B minus A by R will do. Okay. For the moment, just take it that this is the expression that you will get. Once you learn some more of these things, I'll ask you to solve it. Oh, I think it's there in your tube. It's the first question on the second page. Please, your tube copy is in scoops, okay, and online. Whichever you prefer, you can bring that, but do bring it to the tube class. Okay. Where is the gas? Below the inversion. Right? So that's the whole reason. Because things are attractive, the molecules of gas slow down, and slower speeds are in lower temperature. Yes.
Attractive forces, why do we say that the molecules slow down?
That's right. I don't know. Okay. If a molecule is going past another one, right? It's going past another one, and this fellow is attracting it. It will pull this molecule towards it.
So also this molecule will be pulled.
Right. This also will be pulled. So
So
both the molecules will slow down, right? In both the cases it will slow down.
if they are coming closer to each other,
Yes, sir.
then their speeds will increase. That depends on the orientation.
Oh, so head-on collisions, you can very much imagine that how many orientations would be head-on. That's okay. I don't know. You can do that statistics. Okay? Okay, so the thing is that if it does cool down, then how can you practically use it? You could use it as a refrigerant. One of the kinds of refrigerators that you get or you used to get are called Linde refrigerators. These are based on Joule Thomson cooling. So let me just show you what kind of a temperature pressure diagram we are talking of. Okay. Now, we are talking of the upper inversion temperature when we are talking of the van der Waals gases. Okay. There are two inversion temperatures. If we have time, we'll discuss about the other one. If not, just don't bother about it. We are talking of this one. Okay. Above this, there is heating. Below it, there is cooling. So the kind of equation that we have is not a quadratic equation, so it predicts only one point. A better model would predict both of them, and if we have time, we'll do it. If most likely we won't. Okay. So if you have some interest, we could actually do it. But what's very interesting here is most of the gases, most of the real gases, they have their inversion temperature below 300 Kelvin. Okay. So just let me see what is the exact figure. Yeah. So most of the inversion temperature are, sorry, not below, above 300 Kelvin. So at room temperature, most of the gases, they cool down. But look at helium, for example. And once you start doing your projects, you will come across a lot of things called helium cryostats. Cryostats. Okay. These are things that can take you down to roughly about 4 Kelvin. Ideally 4 Kelvin, but most of them would go to 7, 8 Kelvin, 10 Kelvin, something like that. Now, this is based on the compression of helium gas. Okay. So if I really want to cool down helium, how do I do it? If I try to do it at any pressure, start from room temperature. Room temperature is somewhere over there. Huh? That's room temperature, 300 Kelvin. And the inversion temperature of helium is somewhere over here. That's the highest it can come. Yes. So however amount of Joule Thomson cooling I try to do, I'd always be heating the gas. I'll never be able to cool down helium. So what I need to do is to use some other gas to first bring down the temperature to this point, below the Joule Thomson inversion temperature for helium, and then start cooling helium, then start expanding helium through the porous plate. Right? Good. Let's see, if I have time, we'll definitely do the entire thing. Okay.
Then why exactly we need helium? These other gas can.
But all of these have a lower inversion temperature, right? And just one moment. Helium is a gas which liquefies at 4 Kelvin. So you can go all the way down. The others start to condense.
What is it?
Huh? This has nothing to do with liquefaction. This graph does not tell you anything about liquefaction. This is only the inversion temperature is what is shown over there. So if I am working at, it depends on what temperature, pressure I am working at. See, from the equation that I showed you, pressure has no effect. V minus A by RT. There is no term involving pressure. So that particular equation only predicts the upper inversion temperature. Okay. Actually, these are entire things. The entire graph is over here. If I have time, I'll show you the entire thing. Okay. But there's a lower inversion compressor as well. Below this, again, it starts to heat up. That will happen. Okay. So that's it for today. Thank you very much.